let me introduce Lupercio from Mexico, from Kingston, and his talk will be quantum Toric geometry, complex systems, and Mirror Symmetry.
Thank you so much. I'm very honored to be speaking here at HSE again. I think it was 3 years already since I haven't spoken here. Well, it was at the other building, but... in this occasion, I will do a survey talk. And given that we have a tight schedule, because there is a talk at 6 or 6:10? 6:15. I'll do a survey talk, and I'll try to be kind of quick to finish within 45 minutes and have time for the next talk. Okay, so this is a survey of work that I've been doing with many people, and it will show a long talk. So we start here with the so-called sandpile cellular automaton. And this is the following. It is, you are meant to think of a table made of tiny, very small tiles. And they are supposed to be very, very, very small. And the tiles are square, and they completely cover the table. And then at every tile, you write a number. 0, 1, 2, 3, 4, 5, 6, bigger than or equal to 0, an integer number. And it represents, in your mind, the number of grains of sand located at that tile. So, for example, here we have 4 grains of sand, and 3, and 2, and 1. And if I don't write anything, I mean, what I mean is that there is no sand, and the number should be 0. But I just don't write the zeros. And so it's a big matrix with numbers, integer numbers. And then there is only one rule. Only one rule. If you choose a tile, and you can choose it at random. It doesn't matter which one you choose. And then you ask yourself, is the number less than or equal to 3, 0, 1, 2, or 3? If it is less than or equal to 3, then you do nothing. 0, 1, 2, and 3, you do nothing. If it is 4, 5, and higher, then you apply an operation to that tile that is called a toppling. For example, if it is 4, then you think to yourself that there are 4 grains of sand here at this tile, and then the toppling operation means that the tile is too tall then, and then the 4 grains of sand are donated to the 4 neighbors. If there were here 5 grains of sand, or 6 or 7, 6 in this case, then you donate 4 of them to the 4 neighbors. And then that's a toppling. You donate 4 of them to the 4 neighbors, and that's a toppling. And you can do a toppling if it's bigger than or equal to 4, and you cannot do a toppling if it is less than 4. Okay, so we start here. There is 2 places where I could do a toppling. I choose one at random, whichever I want. I chose the one at the top, and then I did a toppling. And then, of course, that 3 became a 4, and there's again 2 places where I could do a toppling. So I choose one of them, I do a toppling, then I choose another one, and I go on and on and on until there is no place where I could do a toppling, until every number is less than or equal to 3.
But this process depends on the sequence, yeah? So if you have 2 neighbor force, then you do first one and then another, and the other way around.
Yes, but it is an interesting exercise for Olympic kids to show that the final state does not depend on the sequence. The intermediate states do depend on the sequence, but the final state doesn't. And that's why some people call this an abelian sandpile, because it doesn't depend on the order of the topplings, of the place of the toppling. So the final state is this one, and it doesn't depend on what order you did the topplings. And that's it. That's the final state. So that's this cellular automaton. It finishes there. That's it. Okay, so now we do an experiment, a computer experiment if you want, or by hand. It might take a while. You put 1,000 million grains of sand at one of the tiles. And you are meant to think that the tiles are so tiny that you have many in the table and you have enough space. Now, if you reach the edge of the table, then the sand goes off and disappears, and that's okay. So it just disappears. So you have 1,000 million grains of sand at the center. And then you do all the topplings. It's a lot of them. Takes a long time, even on a computer, even on a supercomputer with hundreds of processors. And then this is what you get after you do all these topplings. And this was discovered by the physics community, by the physicists doing experiments. And well, it's a very nice structure. It obviously has some fractal nature to it. Has a lot of structure there. And one would like to know what's going on. So if one zooms out into one of the little corners of this structure, then you see this kind of picture. And if you are familiar with algebraic geometry, tropical algebraic geometry, symplectic geometry, you are meant to recognize that this is some sort of balance graph, or also known as a tropical curve. So it's a graph, it's one-dimensional, it has vertices, and at the vertices, the directions cancel out. These three directions, or these three directions, or these three directions cancel out. I forgot to say, but it's obvious that here, rather than numbers, the tiles are so small, they are pixels, that I use colors to represent the numbers. And here, well, the same occurs, but then you get these graphs. And these graphs, the three directions cancel out each other out. Also, these look somewhat like triangles. Of course, they have these curves there. And these triangles they are more or less triangles, and they are meant to be somehow analogous to the tropical projective space, a simplex, two simplex. So they are meant to be two simplexes. So somehow this picture has some tropical geometry pictures inside, and this is intriguing, and we want to understand what's going on. This is another example. In this case, now we take a circular table made of square tiles. It's a circular table, and we put 3 grains of sand. All these examples were computed by Kalinin and Shkolnikov. This example. The previous one, well, was known, and then they observed that if we put 3 grains of sand at every point, at every tile of the circle, at every point of the circle we put 3 grains of sand, and then we add 1 more grain of sand at the center of the circle, then we get this graph. Again, at every vertex the directions cancel out, and the structure near the boundary is fractal and complicated. It's a tree that branches out and branches out and branches out indefinitely. And if you follow one of the branches off to infinity, you reach every irrational point in the circle, and exactly every irrational point in the circle, and nothing else. So all the rational points in the circle are never reached, and everything else is reached exactly once through the branches of this graph.
We should make movies.
Huh?
We should make movies from the
There is, but given the time and whatnot, it could take time to show it. But yes, it's easy to show these movies, how this happens. Yeah, they're already there, in fact. In any case, now you take a square and you put trees at every point of the square, at every tile of the square, and now at each one of these points, here, you put an additional grain of sand. And then avalanches occur, lots of avalanches occur, and after all the avalanching subsides, this is the avalanche, and at the end, this is the final state. And again, this is a tropical curve that passes through the points in which we added the additional grains of sand. So somehow, the sand pile is solving a delta bar equation, this partial differential equation, finding a holomorphic curve that passes through the points. So somehow the sand pile is finding this holomorphic curve that passes through the points.
Are they random? Is what's random?
Well, yeah, I mean, you can choose any points, and then you'll get that. They were probably chosen at random here. Okay, so let's try to describe what we're going to do with this. I remind you that the non-commutative torus arises in mathematical physics by consideration of this the Heisenberg commutation relation PQ minus QP equals H bar times I times identity. And by exponentiation, by taking exponentials in the Bale representation, we can think of them as operators, now unitary operators of the form xy equals lambda yx. So it's an algebra. There is a non-commutative algebra of operators. And then in non-commutative geometry, this is also called traditionally the quantum torus. So the non-commutative torus or the quantum torus. So this is called the quantum torus. So it's meant to be the space, the quantum space, the non-commutative space in non-commutative geometry that corresponds to this algebra xy equals not quite commutative lambda yx. When you commute the variables, a scalar appears, a unitary scalar. So this has a geometric interpretation. If you take an ordinary torus and you take the Kronecker foliation, what is the Kronecker foliation? Well, you take the Euclidean R two-dimensional plane, and you take parallel lines of slope lambda. You take all these parallel lines, and then you take the universal cover map into the torus. Well, either lambda is rational, and then every leaf in the rational case is a torus knot of measure 0 in the two torus, or more often, lambda is irrational, and then every leaf is dense. So the closure of every leaf is contractible in that case. It's not a torus knot, just an inverse copy of the real numbers in the torus. And every leaf is dense. The closure of every leaf is the whole torus. And, well, in that case, we have this dense foliation. Every leaf is dense. And the space of leaves of the foliation, if I identify 2 points as being the same, but the equivalent relation of being on the same leaf, the leaf space of the foliation is a non-Hausdorff space in that case. And then to make sense of this from the point of view of geometry, one says that this is a very non-separated stack. And this very non-separated stack corresponds to this algebra. So in general, Alan Kohn has stressed the point That is, we have these manifolds with foliations, and then we take the Wheeler relation, we get this non-Hausdorff space that is meant to be a quantum non-commutative space, and then well, there is a way to produce an algebra to this, for this space of leaves of a foliation that is a non-commutative algebra. At the level of C-star algebras, it's just the convolution algebra of the holonomic groupoid of the foliation. But there is other ways to think about it, as we will show. And but what we can say with this is that a natural atlas for a non-commutative space often will be a manifold that is foliated. So this will give an atlas for a very non-separated stack, the stack of leaves of the foliation. We will want our manifold in this talk, we'll want the manifold to be complex and the leaves to be complex and holomorphic. And then this way we will think of the space of leaves of this foliation as a complex and often color non-commutative space. Okay, so we must insist on the complex structures. I insist. In this picture, I drew everything real, but I really need it to be complex. So I will take the complex torus, and I will take this in C2. I will take these parallel lines to be complex lines, and then I will take the covering map to C star cross C star, given by x dot x, by x cross x, and I will get these foliations that are still, every leaf will still be dense, but now everything will be complex. So I just stress the point that I will not be doing this over the real numbers, but over the complex numbers. And the foliations are holomorphic. So, well, let me now talk very briefly about toric varieties. So you're probably very familiar with this. Anyway, P1 is a toric variety because C star, it's dense inside P1, and P1 is a compactification of C star. You add 2 points, you add 0, and you add infinity. And it is an equivariant compactification of C star. And what I mean by the moment map is just the height map. In this case, it goes to a closed interval. And so this is the simplest example of a toric variety. The diameter of this interval corresponds to the length of this interval corresponds to the diameter of the sphere. So, well, the second simplest example of a toric variety is P1 cross P1. Now we have P1 cross P1. It's just the previous example cross the previous example. And now the moment map gives me a rectangle. This side corresponds to the diameter of the second P1, and this side of the rectangle corresponds to the diameter of the first P1. And then the shape and the size, the area of the rectangle is determined by a choice on the Kähler cone of P1 cross P1. A point in the Kähler cone gives me the particular shape of the rectangle. Now, if I do a blow down, if I take this side and I contract it to a point, I'm taking one of these spheres and contracting it to a point, I get P2, and then the 2 torus is dense inside P2, thereby rational. But now the moment map goes to a simplex. It just goes to this equilateral triangle with vertices 0, 0, 1, 1, 0, 0, and 0, 1, 0. So these are a picture of the moment map. P3, for some reason I will want to call it later on projective twistor space, but it's just P3. I just did a blow down. Well, if I do a blow up on P2 here, I am getting a quadrangle. Of course, this is not exactly accurate, but I'm just trying to represent it schematically. So what I want to say is that the moment map for P2 goes to a triangle. That's all I want to say. At 2 points, that's right. Well, that's the best way to say it. Yeah, that's the best way to say it. And that's all I would need to use rigorously in the next talk. That's all I will need to use rigorously in the next talk. Okay. Anyway, we have P3. And today, that is very schematic what I am saying. All I want you to think is of P3, the picture of the moment map, like this. At every point in one of these vertices of the 3 simplex, the inverse image is just a point. At every point in one of the edges, the inverse image is a circle, and the inverse image of a whole edge is a sphere. The inverse image at every point in one of the faces is a 2 torus, and the inverse image of every internal point or every more generic point is a 3 torus. And this is a typical picture for the moment map of a toric variety. So the inverse image of a particular point is a torus, and the dimension of this torus is determined by the dimension of the stratus. And this is, in general, not a simplex, but a more complicated polytope. A sand polytope would have more faces. It's always dual to the triangulation of a sphere. And this is the picture that I want you to have in mind right now. Now, I explained before to you that the non-commutative torus is just the space of leaves of this foliation and corresponds to this algebra. So, well, now the quantum projective spaces, or a quantum toric variety in general. What do we do to obtain these quantum toric varieties in general? Well, what we do is, in the previous picture, we replace every torus by a quantum torus. And then we glue them back together. So we deform this picture by replacing every torus by a quantum torus, and now we get a new quantum space, a non-commutative space, that corresponds to a non-commutative or quantum toric variety. So we have to change it slightly. So let me explain this. It's a polytope. But let me explain. It's an arithmetic difference. The difference is arithmetic. Not combinatorial, but arithmetic. So, now what's going on exactly? Well, I will compute a full example for projective spaces in the next lecture. But in this lecture, let me just say that now the polytope, in the past, for toric varieties, I didn't say it, but I say it now. This polytope for a toric variety, it's dual to the triangulation of a sphere. That's a combinatorial condition. But additionally, it's rational. The slope of every edge of this polytope is rational. Now, for the quantum toric varieties, it's still combinatorially the same. It's still the dual to the triangulation of a sphere. But what's very different now is that now the slopes of some of these edges may be irrational. And they are irrational if and only if the space is non-commutative And exactly when the slopes are all rational, then you are back in the usual toric variety commutative case. Well, this polytope comes with an embedding into Rn, always. So the slopes inside Rn, with respect to the affine integral structure. Huh? Well, it doesn't matter, even the edges. If just one of the edges has an irrational slope, then it's non-commutative and vice versa. Because traditionally in toric varieties, what happens is that P is inside Qn. But now, if you go off that, then you are in the non-commutative case. Now, again, how am I going to say this in a more rigorous fashion? Well, I'll try to explain, but the inverse image of every point will be a quantum torus of the appropriate dimension. And what I really mean by this, I mean, it's a very non-separated stack, and this has some algebraic interpretation, of course, but you may want to think of it as this having an atlas in which you have a complex manifold, and for the version that I am explaining today, you can think that it's a compact complex manifold with no boundary, together with a foliation, holomorphic foliation, and that there is a map to the polytope that lifts this map because there is a map to this very non-separated stack that is n modulo f. And so at the level of n, the inverse image of a point will be a complex torus with a complex Kronecker foliation at the level of n. What this implies at the level of the non-commutative of the quantum toric variety, non-commutative geometry, is that the inverse image is a quantum torus of the appropriate dimension. Okay, so now in the past, toric varieties were rigid. You could not really form a moduli space of toric varieties as toric varieties. Of course, if you are willing to change the complex structure of a toric variety in a non-toric fashion, you could do things. But I don't mean that here. I mean, as toric varieties, there was no modular space. They were totally rigid as toric varieties. But now, they are no longer totally rigid. Now there is a modular space of quantum toric varieties. So the modular space of quantum toric varieties, it's a complex orbifolds. The modular space of quantum toric varieties is a complex orbifolds. And it has some distinguished points. There are some orbifold points. The rational points in this modular space are the ordinary toric varieties, the classical ones, the commutative ones. And every irrational point in that modular space is a non-quantum, it's a quantum toric variety that is non-commutative, all the irrational points in the modular space. So the modular space of quantum toric varieties is a complex orbital. I fix the combinatorics of the triangulation of the sphere. I fix the combinatorics. But, of course, you can start gluing these modular spaces as you have a combinatorial change and things like that. But the way I want to state it today, let me just say, and the way I'll do the example next time, is just I fix the combinatorics of the triangulation of the sphere. I fix that combinatorial. Just as you fix some combinatorial data in the classic MGN, for the modular space of toric varieties, I will fix a triangulation of the sphere. And then I will have some n that will be a Gerv number. I'll explain that next time. That is analogous G to fixing some combinatorial data for the Riemann surfaces, and n fixing n points. Here I will have, and this is a continuous kind of data, then I will have something very analogous. And the combinatorial data for the toric varieties is a triangulation of the sphere. That's right. That's right. That's right. That's right. Absolutely right. And then I get the quantum Pn, the quantum P2s and quantum Pns. Okay. The Hartleb's theorem is true for quantum toric varieties, and this implies proof very close in spirit to the proof of Battaglia and Safran, but different, of the irrational Macmillan conjecture. The Macmillan conjecture is a statement, not a conjecture anymore, it's a statement that it asks, if I have one of these simplicial polytopes in Rn, embedded in Rn, and I count the vertices, and then the edges, and then etc. So this is an integral vector. And the Macmillan conjecture says, is there a Diophantine equation that only these vectors appearing from these polytopes solve? Is there a Diophantine equation that it's solved by integers if and only if there's one of these convex simplicial polytopes embedded in Rn with this number of faces, edges, etc., etc., etc.? And the Diophantine equations that were conjectured by Macmillan are extraordinarily complicated. And the Macmillan conjecture is a statement that yes, the Diophantine equations are exactly the ones that determine these numbers. And you can prove, in the rational case, it was famously proved by Richard Stanley. And in the irrational case, you can prove it using this theory, using the Hartleb's theorem for quantum toric varieties. So you can prove the irrational Macmillan conjecture. Here, I wanted to give an example. I will have to go a little bit fast. Of how would you produce a non-commutative a quantum P1 or non-commutative P1? And the basic idea is here, if you have P1, the classical P1, how would you deform it into a quantum P1? So what's the idea? What do we do really? What is our geometric invariant theory in this quantum case? Well, what we do is we take these complex manifolds, S3 cross S1, it's a complex manifold, but it's not a symplectic manifold, and it is therefore not a Kähler manifold. It's nevertheless a complex manifold. And we take on this side, we take the Hopf vibration, and we cross it with S1. So we take the Hopf vibration, and we cross it with S1. So we have S3 cross S1, we have here S1 cross S1, and here we have P1. But it turns out that these are elliptic curves inside these complex manifolds. So it's a foliation by elliptic curves of S3 cross S1. It is a foliation by elliptic curves. Of course, elliptic curves are covered by C. They are covered by C. And there are some lattice at every point of P1. There is a lattice of C. There's a tau at every point of P1. There's a tau that gives me an elliptic curve. And all together, they form S3 cross S1. Huh? This map or this map? Well, it shows at every point here, there is an S1 cross S1. Because this is the Hopf vibration. So the fiber of the Hopf vibration from S3 is S1. This is the Hopf vibration. This is the Hopf cross S1. Huh? Well, I won't do it today. Next time I'll do it. Next time I'll define this complex structure. It's not entirely obvious. No, nothing here is unique, but I'm going to construct a particular one. And this is a Calabi-Ekman vibration. This is a Calabi-Ekman vibration that I'm describing. So this is a Calabi-Ekman fibration. This is a complex manifold that is non-symplectic, non-Kähler, with a particular complex structure that I'm going to give it. And then this is P1. This is part of the LBM theory that I'm going to explain next time. LBM theory for Lopez de Medrano, Verjovsky, and Meersseman. This is part of a bigger theory that generalizes precisely this picture. Huh? This? No. This is holomorphic. And this is a holomorphic foliation of a complex manifold that is non-Kähler. And these are elliptic curves. So that's the situation. And now, of course, the complex line, the complex plane covers the elliptic curves. So you can think of it as a foliation by complex lines that wind on themselves. And now you can deform that a little bit holomorphically. And now you get a holomorphic foliation by complex lines of n. Now every leaf will become dense all over the place, and the leaf space of this holomorphic foliation will be a quantum P1. It will be a quantum P1. Do I have 10 minutes or? Yeah. It will be a quantum P1. So that's the way we will construct quantum P1s next. And next time I'll do. No, this foliation is P1. Just the quotient of this by this is just P1. Now I deform it holomorphically a little bit. I'll do it. And now I'll get the same n manifold, S3 crosses 1, complex manifold, 4 manifolds, S3 crosses 1, 2-dimensional complex manifolds, holomorphic. But now the leaves are no longer elliptic curves, but complex lines. And now they are dense. These complex lines become dense, like for the quantum torus. In fact, if I take off the point at infinity and the north and south pole here, this becomes exactly a quantum torus. But I am compactifying a quantum torus in a holomorphic fashion. And that's a quantum P1. If I take off the correct. S3 crosses 1 didn't change. The complex structure on S3 crosses 1 didn't change. I moved the foliation. I moved a little bit the foliation. Still, there is 2 points that I can take off here. Now it's fiber over quantum P1. That's the whole point. That this is an atlas for quantum P1. But it's still here, there is inside a quantum torus, a dense quantum torus. So this is a compactification of a dense quantum torus. Okay, well, maybe next time I talk about the mirror symmetry. Let me just say that for the quantum torus, there is a way to do the Rack-Fukaya category computation. It lives on the cotangent bundle of the torus, and you just deform the usual complex structure by this parameter. And this will give you the mirror symmetry for the quantum torus. So this will give you the mirror symmetry for the quantum torus. Okay, and now well, we can generalize this picture a little bit more, and we can go into quantum tropical geometry. So remember, we can do a Rad-Fukaya category of the cotangent bundle by the form and the symplectic form, and it will give you the mirror dual to the quantum torus. So this Rad-Fukaya category is the mirror dual to the quantum torus. And now we can do quantum tropical geometry. So in tropical geometry, I just remind you with one slide, you do these tropical degenerations where these holomorphic curves become these graphs by taking these logarithms. And, well, this is what I started with the talk. You take these sand piles, and you put this in these sand piles. It's what I just how I started the talk. You have a convex table. You have these tiles on the table. At every one of the tiles of the table, you put 3 grains of sand, and then you add a few grains of sand at some distinguished locations, chosen at random. And so the theorem by Kalinin and Shkolnikov states that in the limit, the tropical sand pile, the sand pile computes a tropical holomorphic curve. So this is what we did here. I just remind you. This. So we put 3 grains of sand at every point of the table. Then we add 1 grain of sand at some locations. We let the avalanches of the sand pile evolve, and then we get a holomorphic tropical curve. That's the theory. Okay, so.
It depends on, so in this example, say, is it possible to get this curve from points?
Yeah, it is the whole one holomorphic curve passing through these points.
But there are lines passing through some of them. So not all of points are aligned edges, yeah?
Yes, all of them. The picture may not be very good, but yes, the holomorphic curve passes through all of them.
So it's possible to compute this curve from quadrants
of the points. Yes. Absolutely. Yeah. Yeah. Yes, absolutely, yes. In fact, that's part of the point. You can choose this particular potential. Very similar to what happens in thermodynamics, but now this is piecewise linear. This is similar to what happens in thermodynamics for probability distributions, but now this is piecewise linear. So how do we define this tropical superpotential? Well, we take the sand pile, and at every point we ask, how many times did you topple in the evolution of the sand pile? And this function represents the answer to that question. How many times did you topple? You renormalize it a little bit. Well, and then you get this concave function, piecewise linear, 0 at the boundary of any given convex set. So this, huh?
It is still independent of the sequence of.
It doesn't depend on anything except on the convex set and the affine integral structure. But just depends on the convex set. Just depends on the convex set. So for the circle, as you project the lines of bending of this surface, you get this graph that we already have encountered before. That goes on and on to infinity, and then it touches exactly every irrational point of the circle, and it misses exactly every rational point of the circle. Okay, now, this gives us a way to approximate every convex set. Because, in the case of the circle, as we slice this surface by level sets, we would get first a square, but then we would get something that has 8 sides, and so on and so forth, more and more and more sites, further approximating better and better and better the circle. So this is what we get for any convex set. By asking this question to the sandpile, how many times did you topple at this point? We get this concave function, and then we get this sequence of Delson polytopes approximating the convex set. And they are a better and better approximation as we tend to the boundary. And so what this gives us is a sequence of toric varieties, because each one of these polytopes represents a classical toric variety. And then we get a sequence of toric varieties. Each one is some blow-ups of the previous one. So we have a blow-up, and then we have this toric variety, we have a blow-up, and then we talk the variety. And we are interested as in the limit of xk. We want to get the limit object of all these toric varieties as we approach the boundary of the convex set. And so the theorem, we're writing it down, is that x infinity, the limit of all these toric varieties, in an appropriate sense, we have to define this limit in an appropriate sense, in a correct category. It is a quantum Kähler space, a non-commutative Kähler space, that it has a dense action of a quantum torus, a holomorphic quantum torus, and it's a holomorphic action. And so this is the converse of a theorem of Atiyah, Guillemin, and Sternberg. They said the image of the moment map is a convex set, Atiyah, Guillemin, and Sternberg. And we're saying for any convex set, we have found a space, a quantum, a non-commutative space, so that the image of the moment map of this non-commutative space is this convex set. The dimension of the omega, you see, because they are all of the same dimension of these polytopes. The dimension is just the dimension you would expect. It's just, if it is in Rn, if this lives in Rn, this is n-dimensional complex, but n complex dimensions. Because all the polytopes are of the...
This picture with this approximation to the circle, to the
convex set, omega.
it was what, in dimension 2 or in
In dimension 2. Well, this works on any dimension. It's easier to prove in dimension 2 and 3, but it works on any dimension. The obstruction to proving this is of Euclidean geometry, given that all this now is defined in terms of convex geometry. But of course, you have to have a good setting to have these x infinity objects. So now you have this x infinity toric, let me call it quantum toric object, quantum toric space, and the moment map to the convex set. So any convex set appears as the image of the moment map, or of a quantum toric space. So what is going on at the dense torus inside the quantum toric varieties? The toric varieties, this is what is going on at the dense torus inside. What is going on is that things that are foliations by torus knots, as this index tends to infinity, they become Kronecker foliations. So in the limit, you get this quantum toric space. And let me just mention in 2 minutes the final result. This is in the so-called self-organized criticality. What Perbach, Xiao Tang, and Kurt Wiesenfeld exhibited in this paper is the following. They took one of these sandpiles, say, for example, this one. Of course, they had much more primitive computers. They took this one that we saw at the beginning of the talk, and now they dropped here and here and here and here, anywhere at random, one additional grain of sand. And then they measure the size of the avalanche that occurred. So they drop a grain of sand here, and then they measure the size of the avalanche. They here, anywhere, and then they measure the size of the avalanche. So they did it successively. And this is what they got. The observation of their paper is that the sizes of the avalanche in a log graph is a straight line. And they more or less measure these slopes. They more or less measure these slopes. Of course, they couldn't do very big numbers back then because the computers they were using in the late 80s, well, or 1987 were not all that powerful. But they still could get this kind of thing. So this, you can think of it as a conjecture that this is the statistical distribution for the avalanches for this sandpile. And it took a long time. In 2016, this conjecture was proved, finally, studying space of trees and, well, many other things. So it really took a long time from the conjecture in 1987 that physicists would call a fact or an observation, and mathematicians would call a conjecture, until mathematicians would validate. Pathiraju, Hanson, and Jarai found formal proof of this fact in 2016. And there were many observations in between. So we thought of playing a little bit with what we have observed. So as you said, of course these curves can be computed by the coordinates of the points. And you can even program on a computer how to find these curves using just tropical geometry rather than the cellular automaton. And so we did on this paper with Guzman, Kalinin, Prieto, and Shkolnikov. And so first you can complicate this graph enough. You add a point, you add a point, you add a point, you add a point. Now you have this complicated graph. And now you can ask yourself, well, now if I add one more point, what will be the size of the avalanche? This is more or less the same as taking this holomorphic curve on P1 cross P1. So conceptually, it would be just taking this already very high genus curve on P1 cross P1, but 10,000 genus curve. It starts to show up there at very high numbers. And now you add one more point, modify the curve to pass through these additional points. You multiply it by a line, and then you modify it a little bit to pass through these points. And then you measure how much the symplectic area changed. And that's the size of the avalanche. So you ask yourself, in the physicist's case, they could do this, but even on computers, this takes a long time because it's a cellular automaton. And this can be used, interestingly enough, in plasma physics and in seismology to do actual simulation of earthquakes and solar flares. And people use these algorithms to do actual simulations. So you can ask yourself, can we do something with this algebraic geometry like that? So you get this very high genus curve, you add a point, you see the change in the symplectic area, and you look at the statistics. And yes, it works. So it turns out that you see self-organized criticality in these algebraic curves. And so, you can compare the cellular automaton and the algebraic geometry version of it, and it works very well. You get the same critical exponents from the physical models, so you get self-organized criticality. And that's all I will say today. It's already very late.